Good day once again, everybody, and we are back together. So, we are looking at question number 2, and this is on chemical bonding. So, this is the part that you guys kind of dread. I know it's a lot of theory, so let's dive right into it so that we can get to the right answers. All right, so they say to us silicon dioxide reacts with hydrogen fluoride as well as hydrogen chloride or hydrogen chloride to form water and silicon fluoride and silicon chloride, okay, respectively. Right, now they say to us, write down a balanced equation for the reaction between silicon dioxide and hydrogen fluoride. All right, so let's see, we've got silicon dioxide plus hydrogen fluoride, and remember they told us that they give us silicon fluoride as well as water. Okay, so we'll have silicon fluoride plus H2O. Now all we need to do is just to make sure that our reaction is balanced, so let's do that. Okay, so if I look at this, I've got 4 fluorides there, so that means I'm going to put a 4 there. So I've got 4 hydrogens, which means I'm going to put 2 over there, 1 silicon, 2 oxygens. I think our reaction is balanced, so you just make sure that what you have on the left hand side, you have the same number on the right hand side. All right, let's go to the next one. Now they say to us, we've got a they say the structure of silicon dioxide is shown. Explain the extremely high melting point of silicon dioxide. Now, I want you guys to note they've given us this structure, and you can see how they are so interconnected with one another. So this forms kind of a giant structure, right? So you've got silicon you've got silicon dioxide forming a giant structure, and this giant structure, in this case, we know that you'll need a lot of energy, so more energy is required. Okay, and please note, anytime that you're talking about melting melting point, in this case, it means that you need lots of energy. More energy is required to separate. Okay, or we can even say to break the bonds, right? The strong, let's say strong covalent bonds, right? All right, so you'll notice that you've got strong covalent bonds. By the way, for you to establish whether something has covalent bonds, okay, when you take the electronegativity of each of them, right, you'll see that when you take the electronegativity of oxygen as well as silicon, you'll get a number that is less than 0.9, and so that will tell you that that's a covalent bond. Okay, right, so let's get to the next question. So they say to us, explain why silicon fluoride is a gas at room temperature while silicon chloride is a liquid. Right, now, ladies and gents, I want you to first note in this case, right, that when you're looking at both, if you're looking at both chloride and fluoride, there are several things that are different between them, right? Firstly, there are things that are common, right? And what is common is that they both come from group number 7 in your periodic table. But you'll see that your fluoride atoms are much smaller than chloride atoms, right? So firstly, we know that both of the molecules would be nonpolar, right? So we know that both they would form nonpolar in this case, so that will be determined by an unequal sharing of electrons, right? So both are nonpolar. London forces and contain London forces, okay, or you can call them dispersion forces, okay. So when we look at, in this case, silicon chloride, we know that it's got a larger, now I want you to think about it, because of the size of the, so if you look at the number of electrons that chloride has as opposed to fluoride, it means that its electron cloud is much bigger. So silicon chloride has a higher, or let me say a larger electron cloud due to its size. Okay, and therefore it will form more temporary dipoles in that case. Dipoles. Okay, right, so that's very important. So as a result, more energy will be required. You'll see every time we talk about intermolecular forces, we always end up with the statement, more energy is required. So remember, in this case, it's not just the fact that they both have London forces, but when you look at fluoride, it's the first one in group number 7, right? I think it has 9 valent electrons, but when you look at not 9 valent electrons, but it has 9 electrons in total, right? So which means you'll have, let's see, 2 and then 7, right? And then when you look at chloride, on the other hand, you'll have 3 electron shells in this case, so which means it would be much larger. All right, so in this case, it would mean that it will form a much larger electron cloud, and as a result, it will have more larger temporary dipoles. Okay, so more energy would be required there. Right, now let's go to the next one. So they say to us the diagram shows the structure of a solid fluorine, right? Now note this is one atom, right? Okay, so in this case, they say circle the correct word within the bracket. They say the particles represented. So what you are looking at are 2 atoms that are bonded together, right? So in that case, they say the particles represented by that in the lattice structure are, so notice those are molecules. Anytime you've got 2 or more atoms that are bonded together, you form a molecule, right? Right, they say to us, name the predominant force or bond that keeps fluorine in the solid state. So I want you to note in that case, we will have London forces. Anytime that we've got 2 atoms that are exactly the same, that are bonded together, it means those are covalent bonds. And when we've got covalent bonds, it means that we will have London forces. Okay, so you can also call them induced dipoles or dispersion forces. Nothing wrong with that. Okay, right, and then we go to the next one. They say fluorine reacts with rhenium, okay, to form rhenium heptafluoride, a covalent compound with a melting point of 48. So notice, okay, sodium, it also reacts with the sodium to form sodium fluoride, an ionic compound with a melting point of 993. Notice, of course, the second one, okay, it reacting with fluoride yields a higher melting point. Okay, right, now firstly they say to us the diagram represents 3 of the substances mentioned above, right? Identify the substances by writing the chemical formula of the element or compound in the spaces provided. So I want you to note, the one is heptafluoride, the other one is just sodium fluoride. Okay, so meaning that you've got one sodium, one fluoride, right? Whereas the other one, for every one fluoride, rather for rhenium, you've got one rhenium with 7 fluorides around it. So this looks like rhenium hepta, and please note hepta is 7. Okay, and then here for every one purple, you've got one green, one purple, one green, and so on. So that tells you this must be sodium fluoride. Okay, right, and then C, were we given something else? I think that should be sodium. Okay, so you can see that you've got just one thing there. Okay, so that means that that's going to be sodium. All right, now they say complete the sentence comparing the electron distribution in different substances. They say in covalent compounds, the bonding electrons are, now note, we note that for covalent bonds, it's an equal sharing of electrons. So the electrons are shared. And in this case, right, when we talk about an ionic bond, okay, we know that we are talking about a transfer of electrons, right? So they are transferred. And finally, in metal, or rather in metals, the electrons, well, we say that electrons become free, or you can say they become delocalized. Okay, this is what makes metals to be good conductors of electricity, because of the delocalization of those electrons. Okay, right, let's get to the last part of this. So they say to us, the diagram below shows the crystal structure of hydrogen fluoride, which is a solid, and hydrogen chloride, which is also solid, in the diagram. Right, En represents electronegativity, and Pm represents picometers, which means that's the size of the molecule. And they say HF melts at a higher temperature than hydrogen chloride. Right, now let's go for it. So they say name the predominant type of intermolecular forces between, right? Now they say hydrogen fluoride. Now I want you to note, anytime we've got hydrogen with any of N, O, or F, we call it the NOF group, right? We know we are always going to have a hydrogen bond. So this would give us hydrogen bonding. Okay, so that's hydrogen bond. And then we've got hydrogen chloride. In that case, you'll see that once you take the two electronegativities, that gives us 0.9. So that is a dipole force. Okay, so that's dipole. All right, now they say to us, refer to the diagrams to explain two reasons why the forces between hydrogen fluoride molecules are stronger than between hydrogen chloride. Okay, right, and please, I want you to note, we know that hydrogen bond is much stronger than dipole. We know that for a fact. Okay, but what would be the cause of that? If you notice that when you looked at hydrogen fluoride, the difference in electronegativity between hydrogen and fluoride, firstly, they have a higher difference in electronegativity. So HF has a higher electronegativity. Yeah, negativity, okay, than HCl. Okay, so when we look at the difference between their electronegativity, so in that case it means that HF is more polar, right? And therefore it is more polar. All right, so remember, the higher the electronegativity, the greater the polarity, right? Okay, so then in that case, what we also need to be mindful of is that when you look at fluorine, right, so there's fluorine there, and there's chlorine over there. What do you notice? The sheer size of it, all right? So fluorine is smaller than chlorine, right? So the second thing that we notice, that fluorine is smaller than chlorine, okay? So in that case, we know that the size of intermolecular force also would be greater, because we know that hydrogen bonding is much stronger than dipole forces. So we know that HF has stronger H bond than dipole in HCl. Okay, and so we know that more energy will be required in that case. Okay, more energy will be required to separate the two molecules. Ladies and gents, I will leave it there. All right, I think that it's really been a good explanation. Please do look at this section a bit. I think it is something that I must still also, just pay attention to, because not everybody understands this section. But for now, let's look at question number 3 in our next video. And thank you to Naledi for sending this to us, and shout out to you. And we will go into question 3. For now, I'll see you guys next time. Sharp, sharp.